Okay, we're going to do energy in ionic bonds today. Last time we talked about how in an ionic compound that you have a crystal lattice. For instance, in sodium chloride, let's say that I use red for sodium and I use blue for chloride, that they appear in a 1-to-1 ratio. 1 sodium for every 1 chloride. And so in a crystal lattice, they're going to be every other ion. In a 1-to-1 ratio. And this is actually going to be a cube. So let me see if I can actually give myself some room here. Pull this down. There we go. So just watch how I set this up, everyone, and you'll see how it's going to look. So you kind of see that this is going to be the face of the cube. Then we have the top of the cube. Well, we got that. We got this here. Oh, it's a little too far out. Got that. More or less, you have a cube. And it's going to be alternating patterns of sodium chloride, sodium chloride, sodium chloride. This is called a lattice. It's a geometric shape, and that's what a lot of ionic compounds look like. This is found in all ionic compounds. Remember, everybody, that an ionic compound is when you have a cation and an anion bonded together. What type of bond holds an ionic compound together? Exactly, ionic bonds. I think it goes without saying that ionic bonds involve ions. Now, here's the new material. During a chemical reaction, energy is either released or absorbed. We will not get into chemical reactions until Unit 8, but you actually did them on your homework recently. This is a chemical reaction. Sodium ion reacts with a chloride ion to yield sodium chloride. This is a chemical reaction. This side of the reaction, the left side, are called your reactants. The reactants are things that you need. It's like the ingredients. And everything on the right side of that yields arrow is called a product. In this case, we only have one product. The product is what you make. If I'm going to make a cake, my reactants are going to be eggs, flour, sugar, milk, cake batter, all that stuff I need to make a cake. My product will be the cake. So sometimes when you have a chemical reaction, energy is absorbed into the reaction and energy is released out of the reaction. Now here's what you all really need to get. You ready? One type of reaction is called an endothermic or endergonic reaction. What does the prefix endo mean? Inside. N-E-N means inside or entering. For instance, mammals have an endoskeleton. Birds have an endoskeleton. This means that energy is absorbed. When something is absorbed, is it going in or is it going out? It's going in. Yes, Arshan.
For crystal lattices, the ionic compound isn't 1-to-1. Is it like different in the like shape of it?
No, it's shaped pretty much like a cube. It's geometric. Okay, now, everybody, that's where it gets a little complicated if you don't pay attention. So, pay attention. We're going to make an XY axis. Your x-axis is time. Your y-axis is energy. Are we clear on that? Crystal clear. Lattice crystal. You start off with energy. That red line is energy. These are your reactants. Let's see what you're able to absorb here. Ha, get it? Another joke. Are your reactants what you need for a chemical reaction, or are they what you produce in a chemical reaction? Reactants are what you need. It is what you start with. You're going to go through a chemical reaction here, and these are going to be your products. Now, just use your powers of observation. What has a higher energy level on this graph? The reactants or the products? That's right. In this reaction, products are at a higher energy level than reactants. Therefore, energy was absorbed. This is an energonic or an endothermic reaction. Energy was absorbed to make your products have more energy than what you started with. So, that is an energonic reaction. Now, let's do opposite. Exothermic slash exergonic reaction. Hold on, I got to respond to one of your classmates that's asking how he's going to do the vocab quiz today. All right. What does the prefix X mean? Outside. A crab has an exoskeleton. A grasshopper has an exoskeleton. The external temperature outside is warm. So X means outside. In this particular process, energy is released. So I want you to draw your XY axis again. X is time. Y is energy. I'm going to get my red line again. Here are my reactants. Now, based on the fact that energy is released, would you expect your product energy level to have more or less energy than what you started with? Less. So it's going to look like this. If you're wondering what that hump in the energy is, That's called your activation energy. It's the energy you need to achieve a reaction and to make product. So if you notice, the product energy level is less than the reactant energy level. This means that energy was lost. The energy level of the products is less than the level of reactants. Therefore, energy was released. You can say it was released, it was lost. Any of those are fine. Okay. So, the bonds formed between cations and anions is always exothermic. So what has more energy when you're making an ionic compound? The individual ions or the ionic compound itself? Yeah. The ions are going to have more energy than the ionic compound. Sodium and chloride by themselves have more energy than sodium chloride does as a compound. So this is how it will look. Na plus Cl, you have NaCl. The product has less energy than the reactants do. Now, what if you were to break this down? Look at this. What if I start with sodium chloride? You're going to release it. What if sodium chloride is going to break down into its ions? Would that be an energy loss or an energy gain? That'd be a gain. It look like this. So when you have a compound and you break it down, like if you put salt into water and it dissolved, it would actually warm up, or actually it would cool down the water because energy is being released. If you were to hold an exothermic reaction in your hand, imagine that. You're holding an exothermic reaction in your hand. Exothermic means that it is releasing heat. Would the reaction feel hot or cold to you? It is releasing heat, so it will feel hot. If you were holding an endothermic reaction in your hand, it is absorbing energy. Would it feel hot or cold to you?
Cold.
It will feel cold. It's absorbing energy into it, which means it's taking energy from you. It's going to feel cold. We will get a lot more into that later in the school year about heat absorbing, heat releasing. All right, we're nearly done. Let's talk about lattice energy. The energy required to separate 1 mole, and I'll explain to you what a mole is. You guys don't know what it is yet. A mole is a unit of measurement for measuring the amount of a substance. Okay. Let's switch gears now and get into naming. I don't think you guys are going to have much problem with naming. Your homework yesterday really demonstrated that you were getting it. Naming ionic compounds is not tough. Okay, let's talk about how you name the cations. You ready? Any cation in groups 1, 2, and 13 just require the element's name. That's it. You don't have to do anything. Just say it. You know, example, hydrogen or magnesium or aluminum. That's it. You don't have to do anything. Put it in the box. However, for metals in the D block that have multiple charges, you have to put the Roman numerals.
Can you put this on your desk?
Just leave it there. Make sure you watch this later so you don't get lost.
Yeah, I will.
All right, when you have metals in the D block that have multiple charges, you must indicate the charge with Roman numerals. You do not have to use Roman numerals for group 1, group 2, or group 13 elements. It's not necessary. Everything in group 1 will always be positive 1. Always. You don't need to make a special notice there, this is hydrogen 1. You don't have to do that. You don't have to say magnesium 2. Magnesium is always positive 2. So you don't need to make that notice. Hey, everybody, magnesium is positive 2. We know. So you don't need to say it. Aluminum, for example, is in group 13. You don't have to say, hey, aluminum 3. You don't need to do that because it is always positive 3. But when you have elements like iron, iron can be positive 1, positive 2, or positive 3. You have to write iron 1, iron 2, or iron 3. You do not have to do this with the polyatomic ions either. Just the metals in the D block, and some of them in the P block, but mostly in the D block, that can have multiple charges. Arshan, you have something you want to say?
How is it like for metals that only have like one charge? All right.
We're going to get to that. That's my next topic. There are a couple that you'll just need to memorize. Yes?
Does that include the F block as well?
The F block is pretty much positive too. We very seldom deal with the F block in this class. So we don't really need to address it. But yeah, it would be the F block too. Most of those are synthetic, so they don't behave as the natural ones do. So Arshan brought up a good point. There are some metals in the D block who only have one charge. Some metals in the D block only have one charge. The two that I can think of, and there's a third one that just is slipping my mind. We'll figure it out later. One is zinc. Zinc is always positive 2. You don't have to say zinc 2.
So that would be just like groups 1, 2, and 13.
Yes. So whenever you have zinc, you do not need to say zinc 2. Not necessary. Zinc is always positive 2. This is one of the little ones you just need to remember. Silver. Silver is always positive 1. So you don't need to say silver 1. Just say silver. It's always positive 1. There's another one that I just brain fart. I can't remember. We'll deal with it when we come across it. But these are the two that you definitely need to know, guys. You do not need to write zinc 2. You do not need to write silver 1. It's a given. Yes, just say same. Zinc, silver. That's it. You don't need to do anything else. Now, when it comes to anions, the monatomic anions. The main ones I'm going to be referring to, I'll list them all here. It's pretty easy. Fluorine, chlorine, bromine, iodine, astatine, oxygen, sulfur, arsenic. What am I thinking? What am I leaving out? Nitrogen, phosphorus, selenium. They all end with "ide." Tellurium, telluride. You change the ending of the name to IDE. Fluoride, chloride, bromide, iodide, astatide, oxide, sulfide, arsenide, nitride, phosphide, selenide, telluride. You change the ending to IDE. You only do this with the ones that are on the periodic table. You do not do this to the ones that are on the polyatomic ion list. And this can actually lead to some issues here. And we experienced some of those issues yesterday. For example, check this out, everyone. What is that ion called? S with a -2 charge. Sulfide. What is SO4 with the -2 charge? Sulfate. And remember what I told you yesterday? When you have a polyatomic ion that has one less oxygen than the ATE, what do you name it? Sulfite. You see how this can cause some issues? You need to pay attention to if it says IDE, ITE, or ATE. It does matter. Here's another example. What is P with a -3 charge? That is phosphide. What is PO4 with a -3 charge? That is phosphate. And what is PO3 with a -3 charge? Phosphite. Let's do one more. What is N with the -3 charge? Nitride. What is NO3 with the -1 charge? Nitrate. What is NO2 with the -1 charge? Nitrite. You need to pay attention to those names because it does make all the difference. If you thought nitride was nitrate, well, look at the charges. Nitride is -3. Nitrate is -1. So that is a really big difference. All right, and last thing I'll put for today, polyatomic ions. You know, the hydroxides, the phosphates, the ammoniums. Don't change any part of the name, period. If it's phosphate, leave it phosphate. If it's ammonium, leave it ammonium. If it's nitrate, leave it as nitrate. That's it. You don't need to change any part. Yes?
This year, are we going to have to deal with ions in protein?
Not really. No. Maybe once or twice, but not often. All right, that's it.